February 2024. The screens at the European Space Agency did not just flicker with a new image, they lit up with an entire universe. For decades, humanity has peered into the cosmos through keyholes. We have used the Hubble Space Telescope to drill deep, narrow shafts into the dark, retrieving agonizingly beautiful, yet isolated samples of the infinite. We have used the James Webb Space Telescope to peer back in time, hunting for the first sparks of creation in tiny patches of the sky. These instruments are snipers, precision tools designed to hit a target billion of light-years away. But to understand the architecture of reality, you do not need a sniper. You need a cartographer. You need a wide-angle lens capable of capturing the terrifying scale of the structure we call home. And on that day, the Euclid mission delivered. The image that materialized was not a single galaxy, nor a cluster, nor a nebula. It was a mosaic. A single, seamless tapestry woven from 260 separate observations. At first glance, it looks like static on an old television set. Thousands of specks of dust scattered across a velvet background. But then, you zoom in. And you keep zooming. And the realization hits you with the force of a physical blow. Every single speck of dust is a galaxy. Every point of light is an island universe, containing hundreds of billions of stars, trillions of planets, and perhaps, countless civilizations that will lived and died without ever knowing we were watching. In this single release, covering a patch of sky that is just a fraction of the full survey, Euclid revealed over 14 million celestial objects. But the headline, the number that broke the minds of astronomers, was the 1.2 million galaxies captured in high-fidelity sharpness. This is the largest, most detailed map of the universe ever created in such a short time frame. It is a portrait of the cosmos that covers an area of the sky 500 times larger than the full moon. If you were to hold a grain of sand at arm's length against the night sky, that is what Hubble sees. Euclid has just opened the shutters on a window the size of a skyscraper. This is not just a technological leap, it is a paradigm shift in how we perceive our place in the dark. To understand why this specific release is shaking the foundations of cosmology, we have to understand what Euclid is actually looking for. It is not hunting for pretty pictures. The beauty of the Perseus cluster or the spiral arms of hidden galaxies is just a byproduct. Euclid is a detective investigating a crime scene. The victim is the universe itself, and the culprit is a force we cannot see, cannot touch, and cannot explain. We call it the dark universe. 95% of everything that exists is made of dark matter and dark energy. Everything we have ever seen, every star, every planet, every cloud of gas, every human being, is just the froth on top of a vast, invisible ocean. For nearly a century, we have known this ocean exists. We can see its gravity pulling on the visible matter. We can see galaxies spinning too fast, held together by an invisible glue. We can see the expansion of the universe accelerating, pushed outward by an invisible pressure. But we have never seen the ocean itself. Until now. Euclid was built to photograph the invisible. By capturing millions of galaxies at once, with a precision that rivals space-based observatories and a field of view that rivals ground-based surveys, it allows scientists to measure the shapes of these galaxies with unprecedented accuracy. This is where the terror and the beauty of physics intertwine. Light, as it travels through the cosmos, does not move in a straight line. It follows the curvature of spacetime. And spacetime is curved by mass. When the light from those distant 1.2 million galaxies travels toward Earth, it passes through vast concentrations of dark matter. This matter acts like a lens, a distorted piece of glass that bends the light, subtly warping the shape of the background galaxies. This is called weak gravitational lensing. To the human eye, these distortions are invisible. A galaxy might look 0.01% more elliptical than it actually is. But Euclid is not a human eye. It is a 600 megapixel camera combined with a near-infrared spectrometer and photometer, designed to measure these infinitesimal distortions across billions of targets. By analyzing how the light of 1.2 million galaxies has been warped, Euclid can effectively draw a three-dimensional contour map of the dark matter lying between them and us. It is like seeing the wind by watching the leaves flutter. We cannot see the wind, but if we track the movement of a million leaves, we can map the storm. The data release we are discussing today is the first 5% of the mission's total survey. Just 5%. And yet, it contains more information than decades of previous surveys combined. The sheer volume of data is difficult to articulate. We are talking about petabytes of information that will take years to fully process. But the initial look, the early release observations, focused on specific targets to demonstrate the observatory's power. One of these targets was the Perseus cluster, a massive structure 240 million light-years away. In previous images, we saw the bright, dominant galaxies at the center. In Euclid's image, we see the background. We see the faint, ghostly light of 100,000 additional galaxies that were previously lost in the noise. We see orphan stars, ripped from their home galaxies by gravitational tides, drifting alone in the intergalactic void. These stars create a faint glow, a ghost light, that Euclid is sensitive enough to detect. This light traces the gravitational potential of the cluster, showing us exactly where the dark matter is piling up. But it is not just the scale, it is the clarity. Ground-based telescopes have wide fields of view, but they have to look through the Earth's atmosphere. The atmosphere is a turbulent, chaotic soup of air that blurs starlight. It is like trying to read a book at the bottom of a swimming pool. Space telescopes like Hubble eliminate the blur, but they have tunnel vision. Euclid combines the sharpness of space with the breadth of the ground. This unique combination allows it to see things that were theoretically predicted but never observed. For instance, in this first data dump, astronomers found evidence of dwarf galaxies that should not exist. Standard models of galaxy formation suggest that dwarf galaxies are messy, chaotic blobs of stars. But Euclid found dwarfs with perfect, spiral structures. Tiny, intricate clockwork mechanisms spinning in the void. This challenges our understanding of how galaxies grow. How does something so small maintain such a complex structure? Is dark matter acting differently on these small scales? These are the questions that keep astrophysicists awake at night. The standard model of cosmology, the lambda-CDM model, is our best guess at how the universe works. It has held up for decades. But cracks are appearing. The rate at which the universe is expanding, known as the Hubble constant, does not match when we measure it with different methods. The distribution of matter is slightly smoother than our simulations predict. Euclid is the machine built to stick a crowbar into these cracks and pry them open. If the universe is a simulation, Euclid is looking for the glitches. If our understanding of gravity is wrong, Euclid will provide the evidence. This first image, this mosaic of 1.2 million galaxies, is the opening statement in a trial that will determine the fate of our physics. We are looking at a slice of the universe that spans billions of years of history. We are seeing galaxies as they were when the Earth was just cooling from a molten ball of rock. We are seeing light that has traveled across the expanding void, carrying with it the fingerprints of the structure of reality. What is perhaps most unsettling about this data is what it implies about the empty spaces. When you look at the Euclid mosaic, your eye is drawn to the bright clusters, the glowing filaments of the cosmic web. But between them lies the void. The great darkness. For a long time, we assumed these voids were empty. Just vast stretches of nothingness. But Euclid's sensitivity is revealing that nothing is a relative term. There are things hiding in the dark. Faint, low-surface brightness galaxies that are so diffuse they are almost transparent. They are like ghosts, passing through the universe unnoticed. Until now. These ultra-diffuse galaxies might be made almost entirely of dark matter, with just a handful of stars to betray their location. Or they might be something else entirely. Failed galaxies. Systems that started to form and then stopped. The release of this data is not just a scientific milestone, it is a psychological one. It forces us to confront the true scale of the cosmos. When you hear 1.2 million galaxies, it is just a number. But when you scroll through the image, when you zoom in on a random patch of blackness and find a spiral galaxy as beautiful and complex as our own Milky Way, sitting there in the silence, you realize the frightening abundance of the universe. We are not rare. We are not unique. We are one of millions in just a single snapshot. And this is just the beginning. Euclid will continue to scan the sky for 6 years. It will map 1/3 of the entire celestial sphere. It will catalog billions of galaxies. It will create a 3D map of the universe extending 10 billion years into the past. We are standing on the shore of a new ocean. The first wave has just washed over our feet, bringing with it strange artifacts and impossible treasures. But the tide is rising. The data coming down from that telescope, parked 1.5 million kilometers away at the Lagrange point 2, is going to rewrite the textbooks. We thought we knew what the universe looked like. We thought we knew how it evolved. But as we look at this first, monumental release, one thing becomes perfectly clear: we have been looking at the universe with our eyes closed. Euclid just told us to open them. As we descend from the macroscopic view of the entire mosaic into the microscopic details hidden within the pixels, the story becomes even stranger. We are not just looking at a static map. We are looking at a violence that has been frozen in time. The interactions between these galaxies, the mergers, the collisions, the silent cannibalism occurring in the deep dark, this is where the real secrets are buried. And nowhere is this violence more apparent than in the heart of the Perseus cluster, where Euclid's gaze penetrated the blinding radiance of NGC 1275 to reveal a structure that resembles less a collection of stars and more a biological anomaly. In the center of this gravitational trap, we see the Perseus galaxy not as a static island, but as a predator caught in the act of feeding. This is what astronomers call a secondary nucleus. It sounds technical, almost mundane, until you realize what you are actually looking at. You are seeing the undigested core of another galaxy, a victim that ventured too close and was stripped of its outer stars, its gas, and its dignity, leaving only a dense, glowing heart spiraling into the maw of the larger host. Standard models predicted these events occurred, but seeing them with such terrifying clarity in a wide-field survey changes the narrative. Usually, to see such detail, we have to zoom in so close that we lose the context. We see the murder, but not the crime scene. Euclid gives us both. It shows us the central act of cannibalism, but it also captures the thousands of smaller, terrified galaxies surrounding the event, distorted by the immense gravity of the cluster. This is the hidden machinery of the cosmos. We used to think of galaxy evolution as a slow, graceful dance. Euclid reveals it is a mosh pit. Surrounding these massive collisions, the telescope detected something even more elusive: intracluster light. This is a faint, ghostly glow that permeates the space between the galaxies in a cluster. For decades, this was just noise in our data, a nuisance to be subtracted so we could see the real objects. But Euclid has shown us that this noise is actually the history of the cluster written in light. This glow comes from billions of orphan stars. These are suns that were ripped away from their home galaxies during violent mergers billions of years ago. They are gravitationally unbound, drifting in the eternal night between the galactic islands. Imagine looking up from a planet orbiting one of these orphan stars. You would have no night sky. No Milky Way band. Just a profound, absolute blackness, punctuated perhaps by the distant, fuzzy patch of a galaxy millions of light-years away. You would be truly alone in the void. Euclid is the first instrument capable of mapping this ghost light with enough precision to tell us how much dark matter is holding the cluster together. Because these stars, while free from their galaxies, are still prisoners of the cluster's total gravity. By mapping where they drift, we map the invisible walls of their prison. This brings us to the true purpose of the mission, the specter that haunts every pixel of these 1.2 million galaxies: dark matter. We speak of it often, but it is difficult to convey how deeply strange this substance is. It is not just matter we cannot see. It is matter that does not interact with the electromagnetic force at all. It does not reflect light, it does not absorb light, it does not emit light. If you were to hold a chunk of dark matter in your hand, it would pass right through your flesh, through the floor, and through the earth, settling only at the gravitational center of the planet. It is a ghost in the machine of reality. Yet, it is 5 times more abundant than the normal matter that makes up you, me, and every star in the sky. Euclid's map is essentially a topographical survey of this invisible landscape. In the images released, especially in the wider field views, we are seeing the cosmic web in high definition for the first time. The cosmic web is the largest structure in the universe. It consists of vast filaments of dark matter, stretching across hundreds of millions of light-years, connecting galaxy clusters like nodes in a neural network. Galaxies tend to form and flow along these filaments, like beads sliding down a string. Between the filaments are the voids, massive, empty bubbles of repulsion. What Euclid has achieved in this first data release is a measurement of cosmic shear so precise it borders on the impossible. As the light from those background galaxies travels toward us, it passes through these dark matter filaments. The gravity of the dark matter bends the light, slightly distorting the image of the galaxy behind it. A round galaxy might look slightly oval. A vertical galaxy might be tilted by a fraction of a degree. By measuring the average distortion of millions of galaxies, Euclid can reconstruct the density and position of the dark matter in front of them. It is like figuring out the shape of a glass lens by looking at how it distorts the scene behind it. The preliminary results from this shear mapping are already raising the hair on the back of astronomers' necks. The distribution of dark matter seems to be clumpier than expected. Standard cosmology, the lambda CDM model, predicts a certain smoothness to the dark matter distribution on large scales. It suggests that over billions of years, gravity should have pulled matter into these filaments in a very specific, predictable way. But Euclid is hinting at a universe that is rougher, more textured. This might sound like a minor detail, but in physics, a minor detail is often the thread that unravels the entire sweater. If the dark matter is clumpier than our simulations predict, it implies that our understanding of gravity on cosmic scales might be flawed. Or, even more frighteningly, it implies that dark matter is not the cold, passive substance we thought it was. Perhaps it interacts with itself. Perhaps it has its own complex physics, a dark sector of forces and particles completely parallel to our own, interacting only through gravity. We are also seeing incredible details in the zone of avoidance. This is a region of the sky that has historically been a blind spot for astronomers because it is obscured by the dust and gas of our own Milky Way galaxy. It is like trying to look at the horizon while standing in a thick fog. But Euclid's near-infrared instruments can pierce through this dust. In this release, Euclid pointed its eye at the hidden galaxy IC342, often called the hidden giant. This is a massive spiral galaxy, similar to our own, but it sits behind a curtain of galactic dust. Previous observations showed a dim, obscured blob. Euclid's image strips away the curtain. We see individual stars. We see the delicate, feathery structure of its spiral arms. We see globular clusters, spherical cages containing hundreds of thousands of ancient stars orbiting its core. The significance of seeing IC342 in such detail cannot be overstated. By studying a galaxy that is physically close to us but chemically distinct, we get a control group for our studies of the Milky Way. We can see how star formation drives the evolution of the galaxy, blowing vast bubbles of hot gas into the intergalactic medium. These winds of ionized gas are crucial. They are the mechanism by which a galaxy breathes. It inhales cold gas from the cosmic web, converts it into stars, and then exhales hot, metal-rich gas back into the void when those stars explode. Euclid is showing us this respiration process in real time. And then there are the failed systems. Among the 1.2 million objects, Euclid has identified a treasure trove of brown dwarfs and free-floating planetary mass objects. These are the borderlands of stellar physics. Brown dwarfs are objects too massive to be planets but not massive enough to ignite nuclear fusion and become stars. They are failed suns, glowing dimly with the heat of their own compression. They bridge the gap between gas giants like Jupiter and red dwarf stars. Euclid is sensitive enough to detect these faint embers in the dark. Even more disturbing are the rogue planets, worlds that have been ejected from their solar systems and are now drifting through the galaxy, untethered to any star. Euclid's data suggests there may be trillions of these nomads. Trillions of worlds, frozen in eternal night, drifting silently through the gaps between the stars. It forces us to reconsider the definition of a planetary system. Is our stable, orderly solar system the norm? Or is the galaxy mostly a graveyard of broken families, with planets cast out into the cold by the violent orbital mechanics of their birth? The sheer variety of objects in this single image is overwhelming. We see ring galaxies, where a high-speed collision has punched a hole through the center of a spiral, leaving a ring of fire. We see irregular galaxies, twisted by gravity into shapes that defy description. We see jellyfish galaxies speeding through the dense gas of a cluster so fast that their own gas is stripped away, trailing behind them like tentacles of blue fire. Each of these represents a unique laboratory for physics. But amidst all this chaos, all this structure, and all this clumpiness of the dark matter web, there is a nagging question. If the universe is so efficient at building these structures, if gravity is so relentless at pulling matter together into these grand filaments and nodes, why are there places where it seems to have simply stopped? The map Euclid is building is a map of presence. It shows us where the matter is. It defines the skeleton of the universe. But a skeleton is defined as much by the gaps between the bones as by the bones themselves. The precision of Euclid's survey brings the empty spaces into sharp relief. We define the filaments of the cosmic web by the voids that surround them. These voids are usually roughly spherical, vast bubbles of emptiness that expand as the matter drains away from them into the filaments. They are the negative space of creation. But as we stare at the intricate, tight-knit fabric of the universe revealed in this 1.2 million galaxy mosaic, we have to ask, what happens when the fabric tears? What happens when we find a void that is too big, too empty, and too old to be explained by the standard flow of gravity? The machinery Euclid has revealed is efficient. It gathers matter. It builds clusters. It weaves the web. So when we look at a map that is 95% structure, the anomalies stand out like a beacon. The data tells us that the universe should be uniform on the largest scales. A homogeneous mix of matter and voids. But there are whispers in the data, echoes from the edges of the survey, that suggest something is violating this rule. A violation that suggests the architecture of the cosmos is not merely a product of gravity, but perhaps of exclusion. If the standard model is correct, matter should be distributed relatively evenly when we zoom out far enough. The peaks and valleys of density should average out. But Euclid is showing us a universe that is incredibly efficient at packing matter into tight, complex structures. The cosmic web is not a loose net, it is a tight mesh. And this tightness makes the existence of supervoids even more baffling. The data streaming from Euclid is confirming that the universe is a crowded, busy place. We are seeing interactions on every scale. We are seeing that even the empty space between galaxies is filled with the faint glow of rogue stars and the warping influence of dark matter. There is no true emptiness in the Euclid mosaic. There is only structure. Structure upon structure, layered in the dark. This realization creates a profound cognitive dissonance when we look at the larger maps of our local universe. Because if Euclid is right, and the universe is a relentless engine of structure formation, then certain anomalies in our sky move from being statistical oddities to being impossible paradoxes. Consider the implications of the dark skeleton Euclid has revealed. We now know that galaxies do not just drift randomly, they are shackled to these filaments of dark matter. They flow along them like cars on a highway. The intersections of these highways are the massive clusters like Perseus. The spaces between them are the rural areas, less populated but still defined by the roads that border them. Euclid's precision allows us to calculate the density of these roads. It allows us to predict exactly how many galaxies should exist in any given volume of space based on the mass of the dark matter skeleton. The math is becoming rigorous. The margins for error are shrinking. This brings us to the edge of the map. The scientific community is currently celebrating the 1.2 million galaxies found in this sliver of the sky. They are marveling at the density. But for those of us who look for the terrifying outliers, this density is a setup for a cosmic horror story. Because if the universe is this dense, if the dark matter web is this ubiquitous, then giant holes should not exist. A hole in a dense fabric is far more noticeable, and far more artificial, than a hole in a loose pile of sand. Euclid is teaching us to read the language of the cosmos. It is a language of gravity, shear, and light. It tells us that matter attracts matter. It tells us that regions of high density get denser, and regions of low density get emptier, but only to a point. The walls between the voids are supposed to hold. The soap bubbles of the cosmic web are supposed to maintain their structural integrity. But we know of a place where the bubbles have popped. We know of a coordinate in the sky where the Euclid data would look not like a mosaic of millions of stars, but like a dead pixel. As we process these petabytes of data, we are building a standard ruler for the universe. We are defining what normal looks like. And normal, according to Euclid, is a universe teeming with light, hidden matter, and complex evolution. It is a universe where you cannot point a telescope without hitting a galaxy. It is a universe where nothing is an illusion masked by dark matter. This makes the true voids, the supervoids, stand out not just as empty space, but as active violations of the laws we are currently rewriting. We are entering an era of cosmology where the mysteries are no longer about what we can see, but about what is missing. Euclid has turned the lights on in the warehouse. We can see the inventory. We can see the dust. We can see the rats in the corners. And because the lights are on, we can now see exactly where the merchandise has been stolen. The map is being filled in, and the empty patches are becoming more distinct, more ominous, and more demanding of an explanation. We have spent this entire journey marveling at the 1.2 million galaxies Euclid saw. We have stared into the face of the Perseus cluster and seen the invisible skeleton of dark matter that holds reality together. We have accepted that the universe is a web of connection, a dense, gravitational tapestry where every thread is accounted for. But to understand the true nature of this web, we must look at the place where the threads have been cut. We must turn our eyes from the crowded, noisy, galaxy-filled sky that Euclid revealed, to the cold silence of the anomaly that defies it. Euclid shows us where 10,000 galaxies are. But there is a hole in the universe, 330 million light-years wide, where 10,000 galaxies should be, but are not. This great nothing is a statistical impossibility that defies the very models Euclid was sent to verify. Was it a 1 in a trillion cosmic accident? Or are we looking at the harvested territory of a godlike Type 3 civilization? Until next time, keep looking up.